All right, this is 13.4, solids. Today we're going to talk about thermal expansion. We'll calculate the change in object size after thermal expansion. Just a couple of reminders. Your test is going to be Tuesday. Your lab is also due Tuesday. So make sure that you do your lab over the weekend, and then you can study for your test on Monday, because I want to make sure you get your review done. One other thing is that the next ACT, I believe it's February 7th. So I've been asked to do a math and science review, which I'll be doing next Monday and Tuesday. Monday will be the math, and Tuesday will be the science. So if you would like to go to these things, please sign up at that clipboard over there on the table. If I don't get a lot of people, then I'll just, if I get like 3 or 4 people, I'll just send them home, because I don't want to teach a class of 2 or 3. So if you're interested, please do that. I don't know how many more I'm going to do. I might do one in March, and that's it. All right, so solids. So far we've talked about gases and liquids. We know that gases don't have bonds between them that keep them together, so they're just kind of moving around because they have heat, and they're moving around and they're nice and free. If we take more energy out of them, they get closer together, and when they're closer together, they form these bonds that create it that phase it down to be a liquid. Eventually, if we take even more energy around it, they actually create more bonds, which make them a solid, and they get stuck into some sort of pattern, which most solids are crystal lattice structures. They have some sort of pattern down at the molecular form. But there are some solids that don't have this pattern, and they're called amorphous solids, which are just like really, really, really slow-moving liquids. They're very viscous. Glass is an example of this. Or the actual ACT, usually like an online thing, places available. Usually, I'm sure it's more than check. There's also different places you can take. All right, so most of the time, these solids get more dense because they're getting closer and closer together as they cool. Let's just say almost every type of material gets more dense as it cools, because gaseous forms, it's like way up like this all over the place. When it's a liquid, it's moving, but it's around each other. And then when it's solid, it's like jam-packed together. The only exception to this is actually ice and water, because I think it's because water is polar. And that's why it's so special. So when it goes into ice, it cools down, it's liquid, it's cool as water, and then all of a sudden it's ice, it goes up into this crystal lattice structure. And because it expands, it becomes less dense, and this is what allows ice to float. And this happens between 4 and 0 degrees Celsius. So ice is less dense than water as long as it's between 4 and 0 degrees Celsius. After it goes below 0 degrees Celsius, now it goes back to being normal, just like all the other substances. It's closer together, and it's more dense than that of water. So if you were to be able to put in like really cold ice, like -10, into the water, it would sink until it warmed up to 0 degrees, and then it would float and start to cool the water around it, so that it's all 0 degrees. So ice is just a little strange. Now, it's good that it does this, because if ice didn't float, then our lakes would freeze at the bottom first, and that would kill all of our creatures there. the pressure.
It freezes from the top down.
Right.
Does that pressure not affect the air?
So like the weight, are you talking about the weight of the ice? Because the ice is the same weight as the water, right? The same amount of mass. So it's not actually adding any pressure to the water beneath it because it's made of the same stuff. It's so it hasn't added any mass, so it doesn't add any weight, which means it doesn't add any pressure. So as long as the creature can live down there with the same amount of water, whether it's ice or water, it doesn't make a difference. But that's a good question. All right, so thermal expansion. Since we know that as you heat this stuff up, as you heat solids into liquids and liquids into gases, they get bigger and bigger and bigger. Well, it's not like all of a sudden they get bigger. It's that as you heat up water, it's starting to take up more and more space because it's more energetic. So it expands. Boiling water is going to take up more space than water just before it turns into ice because it has more energy. So we can calculate this expansion. We have two different expansions. The first one is linear expansion. And so you take like a big long piece of wire, and if you heat it up, it's going to get longer, and if you cool it down, it's going to shrink. So this comes into play when you're looking at power lines. You need to make sure that you give enough slack in those power lines so that when it's really cold, they don't snap. Or when you're making a bridge. Remember when I told you about the bats in the bridge? Remember that from yesterday? I didn't tell you about the bats.
I don't think you know.
Okay, sorry, that's my other class. All right, so the bridges, you've gone over the causeway, right? They got those little cogs parts in the bridge. Well, that's because when it heats up, it expands. And then when it cools down, it contracts. So they need to make sure that those teeth are long enough that when it expands and contracts, the bridge doesn't fall down or it doesn't increase in size and crack due to the pressure. Now, back home, we had a record hot day. It was like 105 or something, which for you guys is like whatever, but for Oregon is quite a change difference. And we had bats living, they live up in the little cracks up there. Well, these bridges were expanding so much that they were actually crushing the bats to death.
Oh.
Yes.
Oh, God.
So is there like bad stuff in the cracks?
There's just like bat blood dripping out of cracks.
Yeah. So, the engineers that did that, they were thinking, okay, well, this is fine for the bridge, but they weren't thinking about the little critters that could possibly be living up there in the future when they built the bridge. So if you're an engineer or architect, you need to think about those sorts of things. And this would be one of the big ones, right?
That's the first thing I'll bring up when I'm building a bridge. There might be bats in the cracks, and then they'll get crushed if it grows. Bats in the cracks. Yeah, bats in the cracks.
So let's look at these equations. I don't like how the equations are set up here. I think they're hard to memorize this way, so I'm going to write them out a little bit differently. Same equation, just a little bit of algebra to them. Now let's go through this. This change, this is how much it changes. So it's either going to expand or contract. This is your initial either length or volume, and it's the O part of it stands for original, if that helps you remember. Initial, it's the same thing. This alpha and beta is the coefficients of linear and volumetric expansion, which are on that little piece of paper that I gave you. One side is latent specific heat, the other side is thermal expansion. So when you need those values, they're right there. And the last is the temperature change. Now this is, remember, final minus initial. Delta is always final minus initial. And they can be in Kelvin or Celsius because it's a temperature change. Now, because we have an initial and a change, most of your questions will ask you, what is the final length? So if you're asked about the final length, you need to make sure that you go the original length plus the change in length, right? So what was it originally and how much did it expand or contract? And if it contracts, it's going to be negative. And it'll show up here because you'll do final minus initial, and if you're lowering your temperature, this will end up being negative. But just make sure that your answer makes sense. With these lengths and volumes, it doesn't matter what the unit is, because this stuff ends up canceling out the units on this side. So if you put in meters, it's going to come out meters. If you put in centimeters, it's going to come out centimeters. Just like here, if you put in liters, it's going to come out liters. If you put in meters cubed or centimeters cubed, that's what it's going to come out as. So you don't have to worry about converting for that part of the equation. They use bimetallic strips in thermostats, and that is two metals stuck together. And they work using this thermal expansion. Because each one of them has its own rate of expansion, when it gets hot, one of them is going to expand faster than the other, which is going to cause it to curl. And then if you cool it, it's actually going to curl in the opposite direction, because one of them is going to contract faster than the other. And it'll be the same one that expanded faster. So it ends up curling. So they use these bimetallic strips in your thermostat, and sometimes they curl them up, like you can see here on this picture. And when you heat it up, it'll actually straighten out. So they can, this curl will be measured, and it'll tell you what temperature it is, because it'll be set to some electronics to do that. Yes.
You ever heard those little paper fish thing that like?
Oh yeah. Mm-hmm.
That's
Same
what that
thing.
reminded me of.
Same thing. Yep. If you heat it up, one side is going to curl faster than the other, because they're two different materials. I know you guys could watch that all day.
Just let us watch it all day.
It's mesmerizing. I stole it off of Wikipedia.
Did you get it checked if it's reliable or not?
It's a picture.
Is it a reliable
Does that
picture?
gift have any vested interest?
What's nice is that I'm a teacher, so I'm actually covered under copyright laws. As long as I only use it for education and I don't redistribute it, I can use it in class.
Thanks.
If I tried to sell this PowerPoint, then I could get in trouble. But as long as I'm using it for education purposes and not redistributing, I can use it. I mean, everybody, they make these pictures and they should get money for it. It makes sense to me. Like, somebody put this together.
It's only one place where people can get paid for pictures.
Those are the kind of pictures you guys should be looking at.
Yeah, Andrew. Stop looking at those.
Okay, so this table is part of it. I gave it to you on this piece of paper, but if you lose it or you don't have it with you when you're doing your homework, it's on page 361 somewhere in the chapter, and it's also at the very back of your book, 914. Notice that here linear expansion is one-dimensional and volumetric is three-dimensional, and most of these are just multiplied by 3, right? The front is 3, multiplied by 3. So one dimension, 3 dimensions. So they're pretty close. Not all of them are perfect, but pretty close. All right, let's do our practice. We have a 700-meter length of copper. It's heated from negative 70 degrees to 150 degrees Celsius. We want to know, what is the copper's final length? I gave you a linear coefficient of expansion, alpha to be 16 times 10 to the negative 6.
It's not a lot. So we have the cost is our soul. Our soul.
All right, 700 meters. What is this?
Initial length.
Initial length, or if you're looking at the equation, L naught. What is this? Negative 70 degrees Celsius. Temperature, initial, good. And 150 degrees Celsius,
Temperature final.
temperature final. And what is this? 16 times 10 to the negative 6.
Coefficient of
Alpha is our coefficient of expansion. What are we looking for? Final length. And we need to find delta L in order to do that. So we're going to use this equation. Plug it in. Delta L is going to be 700 times 16 times 10 to the negative 6. And then final temperature minus initial temperature. Make sure you have that negative, making it a positive. When you do the calculation for this, you should get 2.46 meters. Now I know it's in meters because I put it in meters. To find this final, all I have to do is add up my initial plus my change since it expanded, and I should get 702.46 meters. Now, 700 meters is pretty long, a city block or something, maybe a little longer. So 2.5 meters compared to 700 meters, not really that big. But if you look at 2 meters, it's about 2.5 times my arm length, right? That's a lot.
Yeah, it's quite.
Enough space
That's
to
enough.
fall inside and then get crushed by
Right.
when
You could probably fit a car in there. So if you're thinking about power lines, you need to make sure that you're putting some slack in there for either expansion. So you want to make sure it doesn't get too low to the ground. But also contraction, you want to make sure it doesn't get so tight that it snaps.
That's so low.
All right. Any questions on how to do this?
2.5 meters and you only
No?
have to think
Okay. Here is clicker question 1. I have 4 clicker questions for you today. It will give you some time at the end to do your homework, or at least get started on it. So first clicker question says, an iron bar expands 2 meters when the temperature rises 10 degrees. So if we make that temperature rise 20 degrees instead, how much is it going to expand?